Let's take a closer look at the structure of some compounds that have a carbon-carbon double bond and a carbon-carbon triple bond. So each of these carbons has 3 electron regions, 3 bonded atoms, and 0 lone pairs. So we are going to need to hybridize 3 orbitals together in order to get 3 hybridized orbitals for that carbon. So this is sp2 hybridization, and the shape of this is a trigonal planar shape. There are 3 sp2 hybridized orbitals in a plane, so it's a flat molecule, and they're spaced 120 degrees apart. So here is a diagram showing the valence electrons of carbon before the hybridization takes place. The electron configuration for carbon is 1s2, 2s2, 2p2. So we're just drawing these valence electrons. We have 2 electrons in the 2s orbital and then 2 electrons that are in 2p orbitals. So we are going to hybridize the s and 2 of the p. Before we do that, we'll go ahead and spread all the electrons out. So we're going to take this one and promote it here so that we have 1 electron in each of the orbitals. So these are the ones that need to be hybridized. The energy of the new orbitals is going to be in between these 2 energies. So we have these 3 equivalent sp2 hybridized orbitals, kind of like these 3 lobes in the shape over here. And this remaining 2p orbital does not have anything happen to it. So I'm going to keep it at the same energy, and we have the 2p orbital. So we have 1 electron in each of these new hybridized sp2 orbitals, and then we still have 1 electron remaining in the unhybridized 2p orbital. So these hybridized orbitals look like this shape up here that we just drew. The 2p orbital that is left looks just like a regular p orbital. That's what it is. And that's important because we're going to put these 2 pieces together to kind of paint a picture of how the molecule looks. Alright, so we're going to take this sp2 hybridized carbon, so we have this pizza cut into thirds, and we're going to lay the pizza flat, like on a table. So we're trying to show that this is going back into the screen, this is kind of coming out of the screen, and we have this carbon, this is a carbon atom. And these 3 lobes are the sp2 hybridized orbitals. Let's make the other carbon also look like this. So all of these lobes, these sp2 orbitals, are in this plane. I'm going to try to draw this like a table. Like these are 2 pizzas lying on a table. They are flat inside this plane. And these are the orbitals that connect to the hydrogens. And the hydrogens, remember, have the 1s orbital, the spherical orbital here. So these hydrogen atoms would also be in the plane. They'd be sitting on the table too, attached to these pizzas. Alright, so that's where they are. And these bonds connecting the carbon and the hydrogen are sigma bonds. A line between the 2 nuclei does cross over this overlap portion. So that's what makes these sigma bonds. Remember, the first bond that forms between 2 atoms is going to be a sigma bond. So remember, the carbon, in addition to having these 3 sp2 hybridized orbitals, it also had a p orbital, a 2p orbital, that had not been hybridized. And this p orbital is an axis going through this pizza. So it's going above and below the table over here. So let's draw those. Here's our 2p orbitals above and below the plane. So it's important to point out that this 2p orbital, this is just one orbital. Even though there are two pieces, there's two lobes, that's how a p orbital looks. So this is one 2p orbital. The other two 2p orbitals were used to make these hybridized sp2 orbitals. And these, for these, each of these green lobes is a separate one. So we have 1, 2, 3 green ones. And then the fourth one is this 2p orbital that just happens to have two pieces to it. But this is one orbital. So remember from the energy diagram that we just had, that we had erased, we have the 3 electrons in the sp2 orbitals. So each of these orbitals has an electron in it that is ready to bond. That's why it's bonding to the hydrogen. And then we have 1 electron in the 2p orbital that is ready to bond. So we have an electron in this blue 2p orbital from this carbon and 1 from this other carbon in this blue 2p orbital. And unfortunately, I have drawn these carbons quite a long ways away. So I'm going to have to kind of connect these with like some lines to make them overlap. Kind of stretch them out in this direction. So pretend these are stretching towards one another. So we have some overlap region above and below the plane. That's what makes this a pi bond, because drawing a line from this carbon to this carbon, it goes through this sigma bond, but it does not go through the overlap of this pi bond. So the remaining electrons are in the 2p orbitals. So each carbon atom has a 2p orbital. That's where those remaining electrons are, like the energy diagram shows. And the way they connect to form a double bond, or the second carbon-carbon bond, is a pi bond. It's above and below the plane where the sp2 orbitals are. Let's try a similar process for the triple bond, the carbon-carbon triple bond in ethine. Each of these carbons has 2 regions of electrons that it's making room for. There are 2 bonded atoms and 0 lone pairs. So we need to take 2 orbitals and hybridize them. And the 2 orbitals that need to be combined to make the hybridized orbitals, a set of 2 hybridized orbitals that can accommodate 2 regions, is by combining an S and a P. So this is an sp hybridized carbon. That's what helps give it that linear shape, 180 degrees. All right, let's draw this energy diagram. Before hybridization, the carbon has its 4 valence electrons like this. Let's go ahead and promote one of the electrons so that they're all spread out in these 4 orbitals. We are going to hybridize the S with one of the p orbitals. These 2p we are not going to hybridize, so they stay the same. The new hybrid orbitals are in between the energy of the things that are being added together here. So here are our 2 sp hybridized orbitals, and they each have an electron in it, getting ready to bond to the other carbon, and the hydrogen. So the hybridized carbons look kind of like this. I've sort of drawn them up here. So here are those sp hybridized orbitals, and they form a sigma bond because drawing a line from one carbon to the other passes through this area of overlap. And these sp orbitals over here also bond to the hydrogen's s orbital. So here's the hydrogen here, and here's another hydrogen here. And these are also sigma bonds because the line between the 2 nuclei would go through the overlap portion right here in the middle. So now we've drawn our sigma bonds to our hybridized orbitals. What we have left are the unhybridized 2p orbitals, each with an electron in it. So I'm going to draw one p orbital going above and below the carbon. So these are two p orbitals. And I'm going to try to draw another 2p orbital going in and out of the screen. So here we have one p orbital going above and below the carbon, the green one, that's just one orbital. And then I drew a purple one going in and out of the screen, that's the second 2p orbital. So again, these carbons are pretty far apart, so it's a little bit tough to connect them. I'm just going to draw some lines to show that these are supposed to be close enough to overlap. Over here, this is where the overlap would be above and below the line. The hydrogen, carbon, carbon, hydrogen is all lined up in a straight line. Above and below this line is the overlap of one of the 2p orbitals. And then in front and in back of this line is where the other 2p orbitals would be experiencing pi overlap. This is a pi bond. So this green bond is a pi bond because the line between the carbons does not cross over. And the same thing with the purple one, that is also a pi bond. The first one that we drew, the sp2 hybridized overlap, that one is a sigma bond. There's some pretty good drawings of this in your textbook, and I also have an animation posted on Canvas, so hopefully if my drawings are a little too sloppy, you'll be able to find another one that is more clear. So maybe we should look a little bit at what's in your textbook so that we can review those drawings and compare a single bond versus a double and a triple bond. But hopefully when you take a look at some of these pictures, or if you draw one yourself, you can see that the single bond, it's a sigma bond, and so there is some overlap in the middle, and so it can rotate. So here is ethane, got some hydrogens over here, and this is the sigma bond between the two carbons. It passes right through the area of overlap when you go from one nucleus to another, and this can twist about this one over here. So this sigma bond is in between the carbons, and so one of these lobes can twist around and we still have the same amount of overlap. It does not harm anything to twist this carbon around in a circle if we wanted to. So revisiting our picture of ethene, we have that pi bond that is above and below the plane. So here's our overlap of the pi bond. And if you twist one of these carbons around this axis that's drawn in a dotted line, you have to break this overlap in order to twist and rotate this carbon around this bond. So these pi bonds are not allowing for rotation because they are above and below or in front and in back of the node, and so you would have to break those pi bonds to rotate the molecule. So no, they do not allow for rotation. I'll take another brief look at the molecules in the textbook drawing, so hopefully that will help a little bit. So here is a more colorful drawing in your textbook of the ethene molecule. Again, we have these carbons that are sp2 hybridized with the hybridized orbital in that trigonal planar shape with 120 degrees apart. Those are the ones shown in this golden color. Those are the hybridized orbitals. These are the sigma bonds that are being formed by the hybridized orbital. What's left are some 2p orbitals with one electron on this carbon's 2p orbital, the other one with an electron on this other carbon. And so if these electrons get shared and there's overlap, it's above and below the line that goes between the two nuclei. And so in order to rotate, if we wanted to twist this hydrogen down and this hydrogen up, and we wanted to rotate about this bond, then you'd have to break both this red region of overlap and this blue region of overlap in order to flip it over and get overlap again on the other side. So this one does not rotate.